Hello everyone, today is session 3 for P block elements. We will continue with group 13. Some compounds of boron we will study today, and some compounds of aluminium we will study today, and also the uses of group 13 elements in our day-to-day life. Yeah, so first is borazine, which is also known as borazole. Right, its molecular formula is B3N3H6. Now, this is also known as what? Inorganic benzene. Inorganic benzene, because its structure resembles benzene. Here you can see that instead of carbon, you are having what? Boron and nitrogen alternatively. Right, and this pi bond that you can see here, see this thing. It is actually the donation of lone pair of nitrogen towards empty orbital of boron, right? So this is the cause of the pi bond formation here. So alternative pi bonds are there, and instead of carbon you are having what? Boron and nitrogen, and hydrogens are attached to each of the boron and nitrogen atoms, right? Now next is its preparation. So if you treat diborane with ammonia and you take them in the ratio of 1:2, that means 1 mole of diborane you take and 2 moles of ammonia you will take, you will lead to the formation of borazine. That is known as what? Inorganic benzene, right? Now while you compare the aromaticity of benzene, this you will learn in organic chemistry in detail. So here if you see that benzene is aromatic compound, right? While the aromaticity of inorganic benzene, that is borazine, is less than that of normal benzene, right? And stability also, stability of borazine is less than that of benzene. Or you can vice versa say that borazine is more reactive than benzene, right? So three things can be asked. First one is the aromaticity. So aromaticity of benzene will be greater than that of borazine. Then stability. Stability also, benzene is greater than that of borazine. And then reactivity, if you will compare, borazine, the reactivity is greater than that of benzene, right? Because here the pi electrons are fully delocalized. Here the pi electrons are partially delocalized. They are not completely delocalized over the whole molecule of borazine. Now you answered me some questions which are related to the previous sessions. Right? Question number 1 says borax is, what is the chemical formula for borax amongst first, second, third, fourth? What should be the answer to question number 1? One formula that you can write for it is Na2B4O7.10H2O. What is the other formula for borax, which is related to its structure? What is the formula? Anyone with the answer? Anyone would like to answer for question number 1? What is the chemical formula for borax? So the other molecular formula for borax is what? Na2B4O5OH4.8H2O. This is the chemical formula. Right? We draw the structure like this. B4, then oxygen here, oxygen here, oxygen here, oxygen here, then oxygen here, and then OH on each boron atom, right? So Na2B4O5 OH4 dot 8 H2O is the other formula for borax. Or either you can use Na2B4O7 dot 10 H2O. So answer is 1. Now second question is the bonds present in borazole or inorganic benzene are. How many pi bonds and how many sigma bonds are present in borazine? This is the structure for borazine: boron, nitrogen, boron, nitrogen, boron, nitrogen, and then hydrogen attached. Tell me the number of sigma bonds and pi bonds. I have already drawn the structure for you. Tell me the number of sigma bonds and pi bonds fast. What should be the answer? A, B, C, D. Anyone with the answer? Structure is already drawn. You just need to count the number of pi bonds and sigma bonds. Single bond is made up of only one sigma. Double bond is made up of one sigma plus one pi. Now you tell me what are the number of sigma bonds and pi bonds present in this structure, borazine. Okay. So here we will count out the number of sigma bonds. 1 sigma, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 sigma bonds are there. And what are the number of pi bonds? That will be present only in double bond. So 1 pi, 2 pi and 3 pi. Right? So 3 pi bonds are there. 12 sigma and 3 pi. So the answer will be B. Now attempt this question. When we heat borax strongly, then it will yield the following compound. Na2B4O7.10H2O, when you heat it strongly, that means high amount of temperature you are providing. So which compound or which compounds are being formed? This we have already done. So Na2B4O7.10H2O, when you heat it, you will get Na2B4O7. Then you again heat it, you will get what? NaBO2 plus B2O3. So strong heating gives you these two products, that is glassy bead. So the answer will be 1 and 2, right? Because you're heating it strongly. Now, answer for this question, BOH3 accepts how many OH minus ions? This we discussed yesterday, that boric acid, in spite of having 3 OH, it is behaving as an acid and not a base. So it accepts how many OH minus ions from water? Anyone with the answer? 1, 2, 3 or 4? So BOH3 accepts 1 OH minus ion to give you what? BOH4 negative. Right? So the answer is what? 1. Answer will be 1. Next question is, boric acid is having a polymeric type structure because of its basic nature, acidic nature, hydrogen bonds or coordinate bonds. What is boric acid? H3BO3, the planar structure we did. So it is having a polymeric structure due to which property? Basic nature, acidic nature, hydrogen bonds or coordinate bonds? Anyone with the answer? So here I explained you yesterday that BO3 units are joined by hydrogen bonds, right? These are the hydrogen bonds. So polymeric structure is due to the formation of hydrogen bonds. Next question is, on strong heating, boric acid yields BOH3 or basically H3BO3. When you subject it to heat, what do you obtain? A, B, C, D or 1, 2, 3, 4? What should be the answer? Option 4. Okay. So when you heat orthoboric acid, you will first get HbO2, which is metaboric acid, and then you further heat it. This will give you what? Boric oxide or boric anhydride. So the answer will be B2O3. Third option. Next is number of hydroxyl group attached to boron in borax are. This we have already discussed, right? The structure we drew. This was the structure. So 4 OH groups are attached here. 1, 2, 3 and 4. So the answer will be equal to what? 4. Now next question is Na2B4O7. It is from borax bead test. Borax bead test. Na2B4O7 on strong heating is producing what? NaBO2 plus B2O3. Now, which is NaBO2 is X and Y is B2O3. Now a compound Z plus copper oxide is giving you what? CuBO2 2. That is a blue bead. So what should be Z? Is Z equal to X or is Z equal to Y? Or you are having that Z is a mixture of X and Y with a ratio of 2:1 or 1:2. What should be Z? This is related from... Yes, then you are correct with the answer. Good. The answer is Y, right? Because copper oxide or metal oxide reacts with B2O3 to form bead, colored bead. This is known as what? Borax bead test. Good. Now come on to diborane, the next compound that we need to study here. So boron is forming a number of hydrides, out of which diborane is the most important one, right? Hydrides of boron are called what? Boranes. So how is diborane prepared? You treat BF3 with lithium aluminium hydride, which is a reducing agent. It will convert BF3 into B2H6. See, addition of hydrogen is what? Reduction, right? So here you can see that to boron, hydrogen is being added. That is why lithium aluminium hydride is reducing boron. So it is acting as a what? Reducing agent, right? Whereas the laboratory method, if you will compare, so if you treat sodium borohydride with iodine, you will get what? B2H6 again. So these are two methods by which you can prepare B2H6. So diborane is a colorless and a toxic gas, right? It catches fire when exposed to air. So B2H6 on reaction with air will give you what? B2O3. B2O3 is known as boric oxide, or it is also known as what? Boric anhydride. Boric anhydride. And this reaction is very much exothermic in nature. Here you can see that minus 1976 kilojoule per mole energy is being released here, right? Now, boranes hydrolyze with water to give you what? Boric acid. This also we have discussed previously in the previous session, that some chlorides and hydrides of borane yield boric acid on hydrolysis. Right? So diborane on hydrolysis yields boric acid. Now diborane undergoes cleavage reaction. See how does it undergo cleavage reaction? It has a structure like this. B2H6, in which hydrogens are bridging in nature, similar to as that of Al2Cl6, right? Now what will happen? NMe3 will cleave it symmetrically, like this, right? So it will form BH3 plus NMe3, and here also BH3 plus NMe3. Symmetrical cleavage is there. Similarly with CO also, so BH3, CO and BH3, CO. So symmetrical cleavage is done by NMe3 and CO. Now next, by diborane you can also prepare what? Inorganic benzene, that is what? Borazine, right? How can you prepare that? By reacting B2H6 with ammonia, you will get this adduct with a cation and an anion. You further heat it, you will get what? B3N3H6 plus 12 hydrogen. For example, with NMe3, it was undergoing what? Symmetrical cleavage, right? But with NH3, it will undergo what? unsymmetrical cleavage like this. This is the structure of B2H6. Unsymmetrical cleavage will be done. So this will be like this, right? So BH2 associated with NH3 and BH4 negative separately, right? When you heat this, you will get what? Borazine. Next. So boron also forms a series of hydridoborates. For example, let us say you are having what? BH4 negative. That is tetrahydridoborates, right? So various tetrahydridoborates are known. For example, lithium BH4 or NaBH4. These are also known as borohydrides. These are also known as borohydrides, right? And these are used as what? Reducing agents that you will learn in your organic chemistry. So how these are prepared? You take metal hydride and B2H6, you will get what? Borohydrides. Either you can have lithium or you can have sodium, right? So lithium BH4 and NaBH4 are reducing agents. Now this is very important, bridge bonding in B2H6 molecules. See, actually what happens that BH3 has completed its sextet, right? It has not completed its octet, so it is electron deficient in nature. Now it has two possibilities. Either it forms a adduct like with NH3 or it dimerizes, right? So it prefers to dimerize and forms what? B2H6 to reduce its electron deficiency. Now what happens? See here, if I draw the structure like this, H1, H2, H3 and H4 are terminal hydrogens and HA and HB are bridged hydrogens, right? So this bond involves 2 electrons, this bond involves 2 electrons. These are 2 center 2 electrons. That means the normal bond that is formed here are 2 center 2 electrons only, right? 2 nucleus, boron and hydrogen, and in between 2 electrons are there. So 2 center 2 electron bonds. So these are normal bonds. The terminal bonds are normal bonds. If you see here, see boron is having how many electrons? 3 electrons in its valence shell. 1 electron it has shared in this bond. 1 electron it has shared in this bond. Now you are left with 1 electron only. And here also you are left with 1 electron only. And hydrogen here it is having 1 electron, and hydrogen here it is having what? 1 electron, right? Now what happens is that 2 bonds are being formed, right? So these 2 electrons will form these 2 bonds. This hydrogen, let us say it is switching its position. Sometimes it forms bond with this boron, sometimes it forms with this boron. Then it switches its position, right? Similarly, HB also, what happens here is it switches its position. Sometimes it forms bond with boron and sometimes it forms bond with this boron, right? So what happens due to this switching nature, and this switching is so rapid that we assume that this hydrogen has been bonded to both the borons simultaneously, right? So these becomes what? 3 center 2 electron bonds. These two are what? 3 center 2 electron bond. 3 center boron, hydrogen, boron, and only 2 electrons are used to make these 2 bonds. So that is why it is known as 3 center 2 electron bond. And this type of bonding is known as what? Banana bonding. Banana bonding. You can see here, boron is sp3 hybridized here. Here also boron is sp3 hybridized. Here also the sp3 hybridized orbital is making overlap with hydrogen, right? So this seems like a banana. This forms like this, right? So that is why we call it as banana bonds. Boron, boron, hydrogen. These are 3 center 2 electron bonds. And hybridization of both borons are what? sp3. You can see here, this boron, this hydrogen, this hydrogen, this boron, this hydrogen and this hydrogen are in one plane like this, right? And one hydrogen is above and one hydrogen is below. So it is a planar arrangement. This I have already explained. What is a banana bond? What is 3 center 2 electron bond? This we have. Now talking about the bond lengths and bond strength. So if you compare the bond length, the bridge bonds, that means the distance between the here boron and hydrogen is longer than that of the pair DBH. That means this bridge bond with a normal bond, you will get what? That the bridge bond is having a longer distance than that of the terminal bond. Now next is, if you want to replace hydrogen with methyl, let us say, right? So these hydrogens will be almost unreactive, while the terminal hydrogens will easily go away and be replaced by methyl. That means the reactivity of terminal hydrogen is greater than that of the bridged hydrogen. Right? For example, let us say that I made B2H6 to react with methyl chloride, CH3Cl. So this is the product. This proves that terminal hydrogen are more reactive than bridged hydrogen. That is why they are being replaced by methyl, and these are remaining as such. Now you attempt this question. Select the incorrect statement for B2H6. You have to tell me the incorrect statement for B2H6. Anyone with the answer? You have to select the incorrect statement. See, each boron is sp3 hybridized. We have already studied. It has two types of hydrogens. One is the terminal hydrogen and one is the bridged hydrogen, right? And first one is incorrect because no BB bond is present, right? No direct boron-boron bond is present. The structure is like this, right? So the answer will be first, that it does not contain BB ionic bond. You have to find out the incorrect statement. Okay. Now next question is, diborane can't be obtained from. Diborane cannot be obtained from. So here if you see, if you treat Na2B4O7 with HCl, you will get what? NaCl plus BOH3. That means hydrolysis takes place, right? So Diborane cannot be obtained from the first one because you obtain what? Boric acid here. And other methods we have already done. NaBH4 plus I2 commercial method, BF3 plus LiAlH4 and BF3 plus sodium hydride. These all yield what? B2H6 diborane. Okay. Now we will deal with compounds of aluminium. So aluminium is the most abundant metal found in Earth's crust and it does not occur free in nature. So what are the important minerals of aluminium? Bauxite, already we have done, right? Diaspore, Al2O3.H2O, corundum, Al2O3, cryolite, Na3AlF6, alunite or alum stone, K2SO4, Al2SO4 aluminium hydroxide, feldspar, K2O, Al2O3 with associated with silicon dioxide, mica and kaolinite, right? Amongst these you have to just remember bauxite, corundum, cryolite and mica. These you can remember, right? And other ones are not important from the examination point of view, but you can just have a look at them. Now, preparation of AlCl3 or Al2Cl6. Here also AlCl3 is an electron deficient compound, so it dimerizes to give what? Al2Cl6 to lower its electron deficiency. So how will you prepare AlCl3? Aluminium plus 3 chlorine will give you what? AlCl3. Or you treat it with HCl, you will also get AlCl3 plus hydrogen gases evolved, right? Or you treat alumina with carbon. What happens? That reduction of alumina takes place. Carbon gains oxygen and aluminium reacts with chlorine to give you what? Aluminium chloride. That is AlCl3. Now again, it cannot be prepared by heating AlCl3.6H2O. Here we are dealing with the preparation of Al2O3 and AlOH3. Right? So Al2O3 cannot be just prepared by heating this, because what happens here is that AlCl3 itself gets hydrolyzed by its water. So it forms what? AlOH3. And when you will heat AlOH3, you will get what? Alumina. So this is a preparation of AlOH3 also and alumina also, Al2O3. Now again, here what happens? AlCl3 achieves stability by forming a dimer. Now here 3 center 2 electron bond is not present. However, the structure is same as that of B2H6, but here 3 center 2 electron bond or banana bonding is not present. Why? Because their hydrogen was having only 1 electron. Now here chlorine is having 6 electrons which are involved in lone pair. So it can form coordinate bond also here, right? So coordinate bond is formed here, and this is a 2 center 2 electron bond. This is a dative bond. This is a dative bond. So all bonds are normal bonds, that is 2 center 2 electron bond. Aluminium again is sp3 hybridized tetrahedral in nature. Okay. Now properties, AlCl3, this we have already done. That bottle of anhydrous aluminium chloride, it has white fumes. Why? Because it hydrolyzes in water to give you what? AlOH3 plus HCl, and this HCl is responsible for that white fumes. It behaves as a Lewis acid. Why? Because again it is aluminium is forming 3 bonds with chlorine, so 6 electrons are there, right? And because 6 electrons is there, octet is not completed of aluminium, therefore it behaves as a Lewis acid. It is electron deficient in nature, and due to this Lewis acid character, it is used in Friedel-Crafts reaction as a catalyst, right? So this we will be studying in your 12th class, Friedel-Crafts reaction, Friedel-Crafts alkylation and acylation. In that you will use AlCl3 as a catalyst. Now coming on to Al2O3, so it is the most stable compound of aluminium, right? And it is colorless in nature. However, with certain metals, it acquires color. For example, like ruby, topaz, sapphire, which is blue in color, amethyst, which is violet in color, emerald, which is green in color, they all contain Al2O3. Right? So these are what? Precious gemstones. Now, thermite is what? This you need to remember, that a mixture of aluminium powder, if you will take, and ferric oxide. What is ferric oxide? Fe2O3. Right? If you will take in 1:3 ratio, that is known as what? Thermite. Now next come on to alum, which is called fitkari in Hindi. Right? So alum is what? Basically a double salt. You need to remember this, that it is a double salt. What do you mean by double salt? That when you dissolve it in water, it just breaks into ions. So double salt contains of what? A monovalent cation such as Na plus, K plus. Monovalent means plus, with +1 charges, right? And Y is a trivalent cation. Here you can see that this one will be the monovalent and this one will be the trivalent. Trivalent means +3. Al3 plus, Cr3 plus, Fe3 plus, cobalt 3 plus. However, lithium does not form any alum. This is important, that lithium does not form any alum. So based upon the ions that are present in your alum, you can name the alums. For example, potash alum. Potassium is there, K2SO4, Al2SO4, 3.2H2O, 24H2O. Then sodium alum, Na2SO4, because sodium is there, Al2SO4, 3.24H2O. Then ammonium, so X will be changed to NH4, and ferric. So here you will get it as NH4 2SO4, and instead of aluminium, now you are having what? Fe3 plus here. So this is known as what? Ferric alum. Okay. Now potash alum can be prepared in laboratory also. So if you mix equimolar quantities, means that you will take them in the ratio of 1:1. Right? So 1 mole of K2SO4 you take, and 1 mole of aluminium sulfate you will take, and you just concentrate the solution and crystallize them. So on crystallization you will get what? Crystals of potash alum. This is a preparatory method for potash alum. It is made up of what? K2SO4 and Al2SO4 3. Now uses of group 13 elements and their compounds. So first, you can say that boron fibers are used in making bulletproof vest. So here you can see that although it is a bulletproof vest, but that does not mean that the bullet will, see here you can see that the bullet is basically striking off, and then due to the bulletproof jacket, it is coming back, right? But this is not so, right? This is just a comedy scene from a picture. Here you can see that the bullet is coming back by touching the man, right? So this is not happening in reality. However, what happens is that bulletproof jacket does not let enter the bullet into the person. Here you can see this is a vest that is weared by some policemen, right? To avoid the contact of bullet with the body. So it does not happen that bullet will strike and just went back off. Rather, it will just fall down, or basically does not pass through this jacket, right? And also boron fiber are used for making aircraft material. First is the bulletproof vest jacket. It is somewhat like this, and it is used for making the material for aircraft. Now B10 isotope, it has a special ability to absorb neutrons and form what? B11.5. So it is used in nuclear industry because of this use, right? Now industrial application of borax and boric acid. So borax and boric acid, they are used for making heat resistant glasses, for example like Pyrex, glass wool. Here you can see glass wool picture is there, right? And fiberglass. Now borax is used for making what? Flux for soldering metals. for heat, scratch and stain resistant glazed coating to earthenwares and as constituent of medicinal soaps. And third one, which is very important, that orthoboric acid, if you will take, it is used as a mild antiseptic for eyes. It is used as a mild antiseptic for eyes. Now, here if you will see aluminium, its electrical and thermal conductivity is very much high and it is almost twice as that of copper, right? So aluminium and its alloys basically are used to make pipe, tubes, rods, wires, plates, foils, right? And these due to this properties, basically foils are used for food packing, utensil making. You can use aluminium, right? For making an aeroplane body, aluminium is also taken. For transportation industry also, aluminium is important. However, the iPhone that you are having, that also contains aluminium body, right? So aluminium has various uses and applications. Now, these are some alloys of aluminium. These you don't need to remember as such, right? Only you can remember this aluminium bronze, although we will discuss them one by one. So, aluminium plus copper plus magnesium plus manganese. This is used in aeroplanes and automobile parts development. Aluminium bronze, aluminium plus copper. This is used to make coins and jewelry. Alcalde, it is dura-alumin coated with pure aluminium. It is used in aircraft industry again. Now this is important. Magnesium, as the name suggests, magnesium, calcium and aluminium. It is used for balance beams and machinery. Alnico, aluminium, iron, nickel, cobalt. Again, you can just remember the composition by its name. Right? Aluminium, nickel, cobalt and iron is extra here. So this is used for making permanent magnets. Now, a mixture of aluminium powder and ammonium nitrate is called what? Ammonol. It is used in bombs. So in World War I, you can see here that ammonol bombs were used. Right? And in silvery paints, aluminium is the chief constituent. For fireproof clothes, aluminium sulfate is used, and potash alum is used in purification of water. So that's all for today. We have done group 13 elements in detail, out of which boron and aluminium you need to focus upon. Compounds of boron are very much important. I am repeating their hybridization, their structure, number of sigma bond, pi bond, right? So these you all need to remember, especially the preparation of borazine, diborane, inorganic benzene, or what is inorganic graphite. These you need to remember with structures as well as preparatory methods. So that's all for today. In the next class, we will be dealing with group 14 elements.